specifically even more than that, a local U1. And the message for that was that if you want to impose a local U1, you have to introduce a vector boson. It is neutral, massless, does not have self-interactions. All that is dictated by the local U1, and replace partial derivatives with covariant derivatives, where the gauge boson and its coupling to various fields is dictated up to a single number, the coupling constant. And we gave the example of QED. Then the second ingredient was non-abelian symmetries. For the standard model, there will be two of these, SU2 and SU3. And the main message from that was that if you want to impose a local SUN symmetry on the model, you have to introduce a vector boson that transforms like the adjoint of the group. In the case of SU2, it's a triplet. In the case of SU3, it's an octet, and it's massless. It does have self-interactions, and the self-interactions, as well as the interaction with all the fermions, the scalars that come from replacing the space-time derivative with a covariant derivative, again, for each factor in the product group, depend again on a single parameter, the coupling constant, corresponding to that group. And we gave the example of QCD, local SU3 group, and the quark fields. And now we introduce the third ingredient, which is even more complicated than the previous ones, which is spontaneous symmetry breaking. And I'm not sure whether today or not we will give the model that will demonstrate how that works, the leptonic standard model, which is almost the standard model, but not yet. But let's see the concept of spontaneous symmetry breaking, what it means, what it gives. In particular, in the context, as we'll do along the lecture, of spontaneous breaking of a local symmetry, but not just. So there will be some introduction, and then 3 examples of spontaneous breaking of global symmetry, Z2, U1, SO3. Each of these will demonstrate some features that are common to spontaneously broken symmetries. The fact that spontaneous breaking can lead to fermion masses when initially there were no mass terms from them, and then local symmetries. And just again to make sure the language, the spontaneous breaking of a local symmetry, that's the Higgs mechanism, or sometimes called the Braut-Engler-Higgs mechanism. So we'll see that. So this is a question I asked myself some time ago. I don't know if you ask, so what does it mean, a broken symmetry? Right? It's very strange. What's the difference between having no symmetry and a broken symmetry? Right? What does it mean at all? So in general, indeed, I think there is no meaning in general to broken symmetry. Broken symmetry means you don't have a symmetry, and that's it. But there are 2 cases that I know where a broken symmetry is still more predictive than no symmetry. One is when a symmetry is broken by a small parameter. That small parameter could be a small coupling, a small coefficient in the Lagrangian. It could be the ratio between 2 scales. So, for example, I gave examples of accidental symmetries that hold at a normalizable level. They are broken by non-normalizable terms in all the examples that I gave, and their effect on physical observables that we measure at low enough energies are suppressed by E over lambda. So the symmetry is a good approximation, and we can go further in the accuracy of a calculation by expanding in the small parameter. So we have the symmetry limit, which gives, let's say, zeroth order prediction. Then we can include first power in the small parameter, second power, and that's one case. The other case is, I think for me, was surprising in some sense. It's the case of spontaneous symmetry breaking. So the concept here is that there is a symmetry of the Lagrangian. Okay, that's also the symmetry of the interactions. But the ground state of the universe, the vacuum, the lowest energy state, or the state in which our universe resides, does not necessarily have to share the full symmetry of the Lagrangian. It can have part of it. And this is the case of spontaneous symmetry breaking. The symmetry of the Lagrangian that is not shared by the vacuum. So there is a symmetry of the Lagrangian, but in a sense that we will see concretely what it means, this symmetry is not manifest. But it's right to call it hidden because in what we measure, there are hints that the symmetry is there at the level of the Lagrangian, even though the predictions of a symmetric Lagrangian are different, whether it's spontaneously broken or an exact symmetry that is not spontaneously broken. The thing that surprised me, at least when I realized this, is that the number of parameters, so let's say we have a symmetric case, okay? We impose a symmetry, it's not spontaneously broken. As a result of the symmetry, the Lagrangian has a certain number of parameters. Okay? We saw usually much fewer than in the most general Lagrangian for fields, for the same fields without a symmetry. When it's spontaneously broken, the number of parameters is not different than from the unbroken case. So if you impose the symmetry, the Lagrangian had 3 parameters. Now it's spontaneously broken, which soon we will see what it is exactly or how it acts. The number of parameters does not increase. There are additional terms in the Lagrangian. Terms that were forbidden before are usually now appear, but there are no new parameters. And so the predictions of a spontaneously broken or unbroken symmetry are different from each other. But the predictive power is unchanged in the sense that it's the same number of parameters. And so let's say the new terms that appear, that were not there before spontaneous breaking, their coefficients fulfill relations with the other parameters. There's no introduction of new parameters. So, and these relations are the hint that we are in a situation of a spontaneously broken symmetry rather than exact symmetry. And we'll see that concretely, how it happens and what it means. But in this sense, the number of parameters, then the predictive power of a spontaneously broken symmetry is as strong as that of an unbroken symmetry, even though there are processes that are allowed and were forbidden otherwise. So, symmetries of the interactions are determined or encoded in the symmetries of the Lagrangian, but states, in particular the ground state, don't have to fulfill this. And a well-known example is the hydrogen. The Lagrangian is invariant under rotations, but not all eigenstates of the hydrogen are rotationally invariant. There are these quantum numbers. When you have a finite m, when m is not 0, the state is not rotationally invariant. So there are the symmetries of the interaction, symmetry of the state. It's very generic that when you have degenerate states, then the state at which in the end, or some of the states at which this system is, are not obeying the symmetries of the Lagrangian. And again, we will see that very quickly coming up. So the lowest energy state, we call it the ground state or the vacuum state. And in perturbative quantum field theories, we do here, we expand around the minimum. That's why we use polynomials. I argued this in the very beginning. If the vacuum states is degenerate, namely if there is a degenerate set of vacuum states always the same energy, which is the lowest possible for the system, then we can expand around any of the vacuum states. It doesn't matter around which one we decide to expand. The physics will be the same, whether we expand around one of the vacuum states or another. The fact that the physical consequences are the same for all this set of degenerate states to expand around is a manifestation of the fact that there is a symmetry. But the specific vacuum state, one of these degenerate states, does not obey the same symmetries as the Lagrangian. So we'll see that again very soon concretely. Oops. No. Yeah, spontaneously broken mean no preferences to which of the vacuum state is chosen. And I was collaborating with Helen Quinn. I don't know if you know the Peche-Quinn symmetry, and she liked, I think it's a common example that is given. You have a donkey, he didn't drink for 2 weeks, and now you put 2 buckets, one 2 meters to the right and one 2 meters to the left, exactly the same distance. So, given that there is no preference to either of them, you may think, or you don't think so, but donkeys may think so, that cannot decide. There is zero preference to either, and yet I think we all understand that the donkey will not die out of thirds. It will choose one or the other, okay? So there is a parity symmetry between them, and the donkey will break it spontaneously. He will choose one state and not the other. This is spontaneous symmetry breaking, okay? So if the donkey were a symmetric animal, which I think it is not, probably its heart is also on one side and not the other, but that's the case. And yeah, so as I mentioned, there are forbidden processes, forbidden by the Lagrangian, but after spontaneously breaking, they occur, but they fulfill subtle relations with others, and by this way, even though there are more terms, more processes allowed, the predictive power is not lost and the symmetry is only hidden. It's not completely out of our knowledge. So many of the things I said now will be demonstrated in the simplest example of spontaneous symmetry breaking. And actually, as you see, it always has to do with the scalar potential. And in all our examples, the scalar potential will look more or less the same. Okay, so Z2 and the standard model, spontaneous symmetry breaking, are not very different from each other. So already Z2 is in a lot of aspects useful for our purposes. So again, model building. We take a model with a single real scalar field, phi. That's actually the first model that we gave an example of what symmetry does. Impose a Z2 symmetry, and phi is odd under the symmetry. I remind you that if all the fields are singlets or even under Z2, etc., then there is no meaning to the symmetry, so phi has to be Z2 odd in order that imposing the symmetry will have consequences. And what happens in this case is that the trilinear term in the phi field is forbidden. Any odd power is forbidden, but given that we deal with renormalizable models, that it applies only to phi cube term is forbidden. We have a kinetic term, we have a quadratic term, and we have a quartic term in the field. So phi cubed is forbidden. Mu squared and lambda are real. Why are they real? Because one of the requirements, one of the rules of the game was that the Lagrangian is real, and it's real only if mu squared and lambda are real. Lambda must always be larger than 0, because if it's not larger than 0, then at very large phi values, phi to the fourth term will be the dominant one, and with lambda negative, it will go, the scalar potential, which is minus what is, minus of what is written here, will go to minus infinity. And that means that the potential is not bounded from below, and we want our fields to have a finite value, so we always demand that lambda is larger than 0. But in spite of its name, mu squared can be positive or negative. We call it mu squared just to say that it has mass dimension 2, not to say that it's some mu really squared. Okay? The name of the parameter is mu squared. It's not. Do not separate the mu from the squared, okay? It's not the square of any parameter. It's just dimension 2 in the mass. So far, without noticing it, or implicitly, we always chose mu squared to be larger than 0, and then it has the simple interpretation that it's the mass squared of this field. But we can choose it to be negative, mu squared smaller than 0, in which case it's not the mass squared of the field, and we need to do some exercise because we need to expand around the minimum to understand what is going on. And the minimum now is not at phi equals 0. So how do we find the minimum of the scalar potential? We take the derivative dv to d phi must be 0 at the minimum, and we get 3 extrema, and looking at the second derivative, we understand that one of them is a maximum. So phi equals 0, which is a solution, is a maximum. And there are 2 which are minima. So, and these 2, if you look here, are phi equals plus or minus square root of minus mu squared over lambda. Remind, minus mu squared is positive, lambda is positive, and so there is a positive thing inside the square root, so it's legal, and we call this square root v, and then the 2 minima are at plus v and minus v. So 2 minima, and we have to expand around one of them because that's the minima, and we are expanding around the minimum. And so the value of phi, this phi that appears in the Lagrangian, in the minimum is not 0, and the language that we use for that is that we are saying that phi acquires a vacuum expectation value, or in short, VEV. It means that the value of phi at the minimum is not 0. That's the meaning of that, and usually the notation is left angle phi, right angle, which is the same as the value of phi at the ground state, the lowest energy state of the minimum, and that's different from 0. That's the vacuum expectation value. So we must expand around either phi plus or phi minus. Phi plus and phi minus are related to each other by this Z2 symmetry. It's phi goes to minus phi. It's odd under the Z2. So we have a set, the whole set is symmetric of minima states, is symmetric under the symmetry. But we must choose one of them to expand around. And the physics would not be different whether we choose plus v or minus v, phi plus or phi minus. That's again a consequence of the symmetry that we imposed. The physics is the same, but we have to see what it is. So we choose one of these without loss of generality. As I said, we could choose to expand around the other. Physics would be the same. So around phi plus. And to expand around it, we define a shifted scalar field, phi prime, which is phi minus v. And so the vacuum expectation value of phi prime is 0. Okay, so using phi prime, we are expanding around a minimum. And doing that, replacing everywhere where phi appeared here, phi squared phi 4, replacing phi with phi prime plus v, we get this Lagrangian plus a constant term that I omitted. I don't write constant terms, as I said in the very beginning, they are here, they are legitimate, it's cosmological constant, it does not affect the behavior of the particle, at least not until we consider gravitation. So this is how the Lagrangian looks like, and we used here this relation at the minimum, mu squared equals minus lambda v squared, to write this here and to relate it, and we did not write a constant term. So this is the Lagrangian. The same Lagrangian was Z2 symmetric after expanding around the minimum. And let us compare it to the most general Lagrangian for scalars, which is the first Lagrangian that we wrote. I know it looks a long time ago. It was yesterday morning we wrote it, but so that's what we wrote. It's our first example. This is the most general Lagrangian for a single real scalar field. Kinetic term, quadratic, trilinear, and quartic. And what we have now is kinetic term, quadratic, trilinear, and quartic. All terms in the most general Lagrangian appear here. And in particular, symmetry is not here. Phi prime going to minus phi prime is not a symmetry of this Lagrangian. The existence of a trilinear term is the manifestation that this is a symmetry. So the phi parity originally is hidden. It's spontaneously broken by the fact that we chose one of the vacuum state to expand around. But that's not the end of the story. This Lagrangian, in spite of including all the terms, is not the most general Lagrangian for a real scalar field. Why it is not? Because the most general Lagrangian has three independent parameters, m squared, eta, and lambda. Each of these coefficients of the quadratic, trilinear, and quartic terms is an independent parameter. This Lagrangian has only two parameters in it, lambda and v. All the coefficients depend on lambda and v, not three parameters. Now we have three terms, we have two parameters. It means that there is a relation between these three terms, the coefficient of these three terms. And in this language, this new thing, the eta that was born out of the spontaneous symmetry breaking squared, is 4 times the coefficient of the quartic terms times the mass squared term. So the trilinear term is not an independent, the trilinear coupling is not an independent coupling. So if you measure, I don't know how, but if you measure all three terms and you discover that they fulfill such a relation, the coefficient of the trilinear term squared is related to the product of the quadratics times the quartic, then you understand that you can undo, if you want, this transformation to expanding around the vacuum state back and see that there is a Lagrangian shift with a phi shifted from here that has a Z2 symmetry. So this relation is the hint that it's not just the most generic Lagrangian, but has a hidden symmetry. The symmetry is spontaneously broken. And it demonstrates that the number of parameters doesn't change. There is no new parameter. There are new terms, but no new parameters. And so there are relations. These relations provide us with the clue of a spontaneously broken symmetry and not explicitly broken, namely not absent, not the situation of no symmetry at all. Yeah, so that's the point. I wrote my original Lagrangian in terms of mu squared and lambda. Now I write it in terms of v squared and lambda, but you can do this replacement and go back to the mu squared and lambda of the original Lagrangian. And yeah, so this coefficient now, first of all, this now is positive, okay? 2 lambda v squared times half is positive. In the original Lagrangian that we wrote, we had here minus mu squared with mu squared negative. So it changed sign, it's not the same value, it's not turned from minus mu squared to plus mu squared, it has a different coefficient. so it changed in sign and in size from the quadratic term of the original. This was 0 in the original Lagrangian, and now it's there. So the quadratic and trilinear terms are different between L phi prime and L phi. This coefficient is the same as it was in the symmetric Lagrangian in terms of phi. This would be generic. As long as we deal with renormalizable Lagrangian, the dimensionless coefficients, the coefficients of terms that are dimension 4 in the fields will not be changed, while the dimension full parameters in general will change. We can understand that because the parameter that signifies the spontaneous symmetry breaking is V, the fact that there is a vacuum expectation value. And so the new terms must be proportional to V when they are changed. A dimensionless coupling cannot change by V because it will become dimension full. It can change by V over some scale, but we have no other scale here. If we consider non-renormalizable terms, they would be suppressed by a new scale, 1 over lambda, and then what's here, a dimensionless coupling, could change if we included also non-normalizable terms. As long as we do not, and we will not for some time now, then always the dimensional couplings remain unchanged. The dimension full ones will change. So there are two ways to write this model, or the consequences of imposing Z2 on a theory or the model with a single real field and with the quadratic term coefficient negative. One is to write it in the original form with mu squared negative, and one to write it this way. They are both legitimate, both give the same physics as long as you insist that mu squared is negative. And one of them, this one, is one where the symmetry is in your face, okay? Symmetry is manifest. The other one is good for understanding what's the phenomenology. What kind of spectrum and interactions are there? So both of them are legitimate for different purposes. And we have to look at this to understand what the model describes. It describes a massive scalar particle of mass squared 2 lambda v squared, and which has trilinear and quartic self-coupling with a relation among the mass, the trilinear and the quartic couplings. That's what this model is about, and that's its phenomenology. That was example 1, and now the second one, a U1, still the same features and perhaps more will appear in this second one. So now U1 is an example of a global abelian continuous symmetry that is spontaneously broken. So we take a model, we impose a U1 symmetry. The model has a single scalar field that is complex, however, and we assign it a charge, as we should, under the U1 symmetry, and simplest thing, charge 1. So again, this was, I think, the second example of symmetry consequences that we gave. So we wrote these things already. No trilinear coupling, all quartic couplings, there is just one legitimate, and the mu squared term here. As before, lambda should be larger than 0 for the potential, scalar potential to be bounded from below. But mu squared can be larger or smaller than 0. Mu squared larger than 0, we encountered already, then it's just the mass squared of the complex field. Mu squared smaller than 0 is what interests us. Now, yes, this is taken from some book or review, I don't remember which, apologies to the authors. So with mu squared equals 0, the scalar potential looks like that. It has a minimum at 0. And the second derivative with respect to phi at the minimum is the mass, and that's mu squared. So that's it. How does the scalar potential of a complex field, so this is the complex plane, the scalar potential as a function of real and imaginary, It's usually described in the community as a sombrero hat because of this. So it has this maximum at 0, and it has here a full circle in the complex plane of degenerate vacua, degenerate vacuum state. So the U1 symmetry, which is a phase change of phi, takes you along this minima. Okay, this set, the full set, has a U1 symmetry. You can go from one set to another by a U1 transformation. No matter where you are along the circle, the physics is the same. But you must choose a minimum to expand around. So let us define, first of all, v squared equals minus mu squared over lambda. So I said, no matter what the model is, it's almost always this form of the scalar potential, including in the standard model. Actually, it's exactly this form in the standard model. We can rewrite it, again, up to a constant term that is of not much concern to us, as lambda times phi dagger phi minus v squared over 2 squared instead of that. And from this, it's easy to see that we need phi dagger phi to have a value of v squared over 2 at the minimum. And all states around here have this value. We have to choose one of them to expand around. So now, by making things simple, let us complicate them. So instead of using the complex field phi, let us write it as 1 over square root of 2 phi real plus I phi I. It's for a good purpose, not for complicated things, so that's why I do it. And the U1 symmetry in this language is an SO2 symmetry, right? Before we went the other way around, we started with 2 real fields and imposed SO2, and then we realized it's the same as a single complex field and imposing U1. Now, for a reason, we go back to the SO2 language, and this is how the Lagrangian looks at the SO2 language. Again, we saw it. And in this language, the vacuum expectation value of phi right squared plus phi I squared is v squared. This, again, 1 over square root of 2 makes the difference between this, that phi dagger phi has a vacuum expectation value of v squared over 2, while phi r squared, phi I squared is v squared, not over 2, okay, because of that. It's the same. So in the phi r plane, there is a circle of radius v that corresponds to minima of the potential. That's what we saw on the sombrero picture, previous transparency. So this is what is required, and we choose one state, and the state that is always chosen. So yeah, it's not the only possibility. All possibilities are okay, but is to have the vacuum expectation value in the direction of the real component of the complex field and have the imaginary phi I be 0. And now we want to expand, use fields whose vacuum expectation value is 0, so we expand around the minimum. So to do that, we have to shift, in this case, the real part, and so we define a new field H, which is phi r minus v, and if phi r has a vacuum expectation value v, then H has a vacuum expectation value 0. For no good reason, the community or the literature usually also changes the name of phi I, even though it's the same. So this is the letter Xi. I don't know how experienced you are with Greek letters. When you do a lot of particle physics, in the end, you get to know most of the Greek letters, and sometimes you run out of Greek letters for your notations because there are too many parameters in particle physics. Anyway, this is Xi. And given this and that, then the fields H and Xi both have vacuum expectation value 0. And so we rewrite the Lagrangian in terms of H and Xi, which means that we are expanding around the minimum. There is a kinetic term for H, a kinetic term for Xi, a mass square term for H, a trilinear coupling H cubed, a trilinear coupling H Xi squared, and a quartic coupling H squared plus Xi squared squared. So what does it mean? So So here it's again this Lagrangian. First of all, no SO2 symmetry between A's and Psi. The fact that we have this trilinear term demonstrates it. Also the fact that we have mass squared term for H squared but not for Psi squared also demonstrate. So the SO2 symmetry is spontaneously broken, trilinear term. And what the quadratic terms mean is that we have one massive real scalar H, whose mass squared is 2 lambda v squared, right? For real field, this is half of the mass squared, so the mass squared is 2 lambda v squared. And since there is no mass squared term for psi, psi is massless. And that demonstrates something that I said earlier today. A symmetry means, non-abelian symmetry means that you cannot distinguish between members of a doublet. Phi r and phi I are a doublet originally of SO2. They could not be distinguished if the symmetry is not broken. H and psi can be distinguished. H is massive, psi is massless. There are additional things that distinguish them, but that's the simplest thing to immediately see. So the symmetry is broken. These two scalars are distinguishable. We can tell whether in the physical process it is H or psi that took place. And so now they are distinguishable. And as I said, mass squared is usually the second derivative of the scalar potential. So in a minimum, in this minimum, there are two directions in which you can go. So H is the second derivative along the direction that goes immediately up or is orthogonal to the circle around. And here the second derivative is this 2 lambda v squared. But there is here a flat direction. So if you look at the second derivative in the direction of the circle, it's 0. And that's the psi degree of freedom. The second derivative of the potential in that direction is 0. And so that's why we have a massless scalar field. Actually, there is a deeper reason that can be formulated. We'll see it in a minute, I guess. So, again, the Lagrangian, even though, well, not all terms appear, but in any case, it's not the most general Lagrangian for two real scalar fields, because in spite of having all these terms written here, 1, 2, 3, 4, they depend, or actually 5, because these are two different terms, h cubed and h psi squared. It depends on only 2 parameters, which is the same number of parameters that were in the original SO2 symmetric Lagrangian. And so it means that there are many relations between the various coefficients of the terms. The dimensionless quanticoupling, the dimension is again unchanged. So that's again demonstration, renormalizable Lagrangian, spontaneously broken symmetry, no change in the dimensionless, but all the dimension full parameters have actually changed. We chose to put the vacuum expectation value in the direction of phi r, but we could put it in the direction of phi I or somewhere in between, where both carry vacuum expectation value as long as d squared plus d squared is v squared. The physics would be the same. And finally, why psi is massless? That's a consequence that I mentioned, one of the consequences of, I wrote that abelian or global symmetries lead to charge conservation. Spontaneously broken global symmetry leads to Goldstone boson. I mentioned this fact. This is just demonstration of that. It's a general result of something called the Goldstone theorem, which states the following: the spontaneous breaking of global continuous symmetries is accompanied by massless scalars. So we could not explain massless scalars by symmetries imposed on the Lagrangian. We can explain, if we observe massless scalar, if they are the Goldstone bosons of a spontaneously broken global symmetry. And the number of Goldstone bosons is related to the number of generators that are broken. So with a abelian symmetry, there is always just one generator, so just a single Goldstone boson. But we'll see an example where there are more, and that can happen in various larger symmetries. Third example, SO3. So SO3, I bring it here because we have good intuition for SO3. SO3 is rotations in three-dimensional space. And it means SO3 that you don't have a preferred direction. Okay? All directions are the same. That's invariance under rotations in three-dimensional space. If you define a single preferred, there is something, magnetic field or whatever, in a given direction, then you break the SO3, but if you define a single direction, there is still a symmetry to rotations in the plane perpendicular to the direction that you chose, namely SO2. So breaking or defining a preferred direction in the three-dimensional space would break SO3 to SO2. So that's what we do here, except that these are not space-time now, but internal symmetry. So we impose SO3, and we take a real scalar field which transforms as a triplet of the SO3. So this is the transformation law. LA are the generators of SO3 symmetry, and actually we know, these are the structure constants, we know what they are. It's the antisymmetric tensor in three-dimensional space. So A, B, and C run from 1 to 3. Epsilon 1 to 3 is 1. Any permutation of two indices make the opposite sign. And if two or more of the indices are the same, then epsilon ABC is 0. So we know what these numbers are. And the Lagrangian under SOC symmetry with such a real scalar field is given here. Kinetic, quadratic, quartic, no trilinear term due to the symmetry. I'll repeat it again and again. Mu squared and lambda are real, for the Lagrangian to be real. Lambda always larger to 0 to have the scalar potential bounded from below. Mu squared could be positive or negative. If it's positive, the symmetry applies, and the three components are indistinguishable, and all of them have a mass mu squared, and we cannot tell which one took part in a given process. But we choose the other possibility, mu squared smaller than 0. Define again v squared equals minus mu squared over lambda. And so the scalar potential in terms of v squared can be rewritten as lambda phi transpose phi minus v squared squared, which means that the vacuum expectation of value, the absolute value, is v, but it could be, there is a sphere now of radius v around the origin of the phi 1, phi 2, phi 3 space, and can be on any point on that sphere. So we have a triplet. A triplet is a vector in a three-dimensional space. Okay, it has three coordinates, x, y, and z in space-time, or phi 1, phi 2, phi 3 in this example. So fixing a vector, giving it a value in the ground state, means that we defined a direction in this three-dimensional space of phi 1, phi 2, phi 3. And then what's left is symmetry under two-dimensional rotations in the plane perpendicular to the vector that we chose. So, example, we choose the vacuum expectation value to lie in the phi 3 direction. So phi 1 and phi 2 have vacuum expectation value 0. Phi 3 have vacuum expectation value v. And defining this way, that, sorry, phi 3 is in this way, when we shifted it, we are expanding around a minimum. So all three now, as we wrote this one as phi 3 plus v, have vacuum expectation value 0. And it breaks the SO3 symmetry into SO2 symmetry of rotations in the phi1, phi2 plane. So let us see what comes out of that. So there is the kinetic term for everything. There are terms quadratic in the fields, trilinear in the fields, and quartic in the scalar fields. The quadratic term is this, minus lambda v squared phi 3 squared. And so that already tells us the spectrum. The spectrum has a single massive scalar, m3 squared is 2 lambda v squared, and two massless scalars, because there is a mass square term only for one of the three, for phi1 and phi2. We do not have mass square terms, so m squared 1 and m squared 2 are 0. And that's a demonstration of the Goldstone theorem in more detail. SO3 has 3 generators. SO2 has just 1 generator. And so 2 of the generators are broken at the ground state. And that, by Goldstone theorem, should lead to 2 Goldstone bosons, 2 massless scalars. And this is just showing this explicitly. There are 3 linear terms that were not there before for the symmetric Lagrangian that immediately shows that SO3 is broken. Also this shows that SO3 is broken because you can distinguish at least M3, phi3 from the phi1 and phi2. You cannot distinguish phi1 and phi2 from each other because you have an SO2 symmetry. So all terms should, as you see here, treat phi1 and phi2 in the same way. The 3 linear couplings are exactly the same, and the quartic terms remain the same as in the original Lagrangian. Dimension couplings are unchanged. So I bring this example first because it has some intuition, and second because it demonstrates that the number of Goldstone boson is related to the number of broken generators. Broken generators is related to the transformation that is no longer an invariance of the theory that is broken. Fermion masses. Okay, so that were 3 examples. When we move to the model that is related to nature, what I call the leptonic standard model, it will be a bit more complicated, but still many of these principles demonstrated here will apply there. Fermion masses. So what we want to demonstrate here is that we may have in our theory chiral charged fermions. So the mass terms are forbidden. In the symmetric Lagrangian, we do not have mass terms for these fermions, neither Majorana nor Dirac. But when we take into account spontaneous symmetry breaking, then we may learn that they are actually massive. So let's take an example. We impose a U1 symmetry. We take a left-handed fermion with charge plus 1, right-handed one with charge plus 2. So they are both charged, and it's chiral because we cannot match them to transform the same way under the U1. And a scalar with, not by chance, but with a purpose chosen to have charge plus 1. So, as I said, the fermions are charged and chiral, and so what we call L psi, all possible mass terms for the fermions are forbidden. No mass terms. We do have the kinetic terms for all the fields. For the scalar potential, because it transforms under U1, only the quadratic and the quartic terms. And we have a Yukawa. So the reason that we chose this charge to be plus 1 is to have this combination with sigma of q equals 0. So plus 1 for phi, minus 2 for psi right bar, plus 1 for psi L. Altogether, the sum is 0, and we are allowed to write these Yukawa terms and its Hermitian conjugate. Phi dagger, psi left bar, psi right. We must write it for the Lagrangian to be real. Mu squared and lambda are real. Lambda must be larger than 0. Scalar potential bounded from below. Mu squared can be positive or negative. positive was interesting yesterday, negative is interesting today because we are dealing with spontaneous symmetry breaking. And so the minimum of the potential is not at phi equals 0, but away from it, and we want to expand around it. So there is a whole circle of real phi and imaginary phi of minima, and we make a choice of a vacuum state. So we put the vacuum expectation value, or is in the direction of the real field. And so we take this phi and write it as 1 over square root of 2 v plus h plus ixi, as we did before for the u1. And we get kinetic terms. They remain canonically normalized now in terms of psi left, psi right, h, and xi. So I do not write them explicitly. We've seen that. A scalar potential for h and xi, exactly like the one we saw in the u1 example before. So I don't write it back, and xi is massless and h is massive. And now when we replace in phi here in the Yukawa, we get 3 terms. One is related to v. So in phi there is v over square root of 2. So we get y, the coupling here, times v over square root of 2, times psi right bar psi left. We have h over square root of 2, that's here. And we have I sigma, I xi over square root of 2. So that's the third term plus the Hermitian conjugate. And what we have here are 2 Yukawa terms, one for h and one for xi, and a mass term that was not there before. Right? This is now a quadratic term. Oops. No, the other direction. Yeah. It happens because I think I lost the laser again. I press it too many times, so batteries. Right, so this does not have a scale, it just have 2 fermion fields, so it's a mass term. Yeah, so this is again the Lagrangian. And what we see is we have a Dirac mass term. It's psi right bar, psi left. It's not a Majorana mass term. And the mass, the Dirac mass, psi left and psi right combine into a Dirac fermion, and the mass is yv over square root of 2. How is it possible? Originally, these 2 fields were in a chiral representation, and that symmetry under which they were chiral is broken. And so what is important now after spontaneous symmetry breaking, or taking into account spontaneous symmetry breaking, is the transformation properties under the remaining subgroup, which here there is none. So most generally, and we'll see that explicitly later, if you have a spontaneous breaking of a symmetry G to a subgroup or nothing H, fermions that are chiral under G can acquire Dirac mass if they are vector-like under H and the subgroup H, and Majorana masses if they are in a real representation of H for a non-abelian group. And we'll see more examples. This was just to demonstrate the fact that fermions that are chiral and charged under the group that we imposed can become massive if there is spontaneous breaking, and if they are either neutral or in a real representation of a non-abelian group, or in a vector representation of the remaining non-abelian group. So we'll see all of that with more examples later. So far things were easy. Okay, so it's global symmetries. Now we go to local symmetries and the Higgs mechanism, which is interesting, I think. So we saw that a spontaneous breaking of a global continuous symmetry gives us massless Goldstone boson. Ng stands for Nambu-Goldstone, sometimes they're called it this way. And their number, and actually also the quantum numbers, are in correspondence to the generators that are broken. Broken generators, should I explain? Okay, we'll explain it later. What we'll see now is that the spontaneous breaking of a local symmetry generate mass terms for the gauge bosons that correspond to the broken generators. So intuitively, this seems very surprising in a sense. With a global symmetry, we get massless fields, and with a local symmetry, we get massive things that were massless before. So how and why does that happen? That would be explained in what comes next. So we'll see. These two things are actually related to each other. And actually it's written here, so I'll give you the final answer, but okay. So a massless vector boson has 2 degrees of freedom, 2 polarization. A massive vector boson has 3 polarization, so it has 1 more degree of freedom. Where we change by spontaneous breaking from 2 to 3 degrees of freedom, where would this 3rd degree of freedom come from? It turns out that it would come from exactly the would-be Goldstone boson. Instead of being massless scalars, they become the longitudinal component, the 3rd one that is missing for massless vector bosons. They become, or their derivative becomes, as we'll see explicitly, this missing polarization of the vector bosons. So what is perhaps originally a massless vector boson with 2 degrees of freedom and a scalar with 1 degree of freedom, so altogether 3 degrees of freedom, when the symmetry is, a local symmetry is spontaneously broken, these 3 degrees of freedom combine into the 3 degrees of freedom of a massive vector boson. We'll see that mathematically soon, but that's the physics of it, and we'll see how it works. So let's see the mechanism of spontaneous symmetry breaking of a local U1. U1 is the simplest always example of a continuous symmetry. So we impose a U1 symmetry and we take a complex scalar field phi charge q equal 1. We've seen that several times, I think. Local U1, we must introduce a vector boson, a photon field if you want, AMU, and replace space-time derivatives with covariant derivatives. So instead of just d mu phi, d mu plus ig a mu on phi, with a specific transformation law for a mu under the U1 symmetry. And the Lagrangian is kinetic terms for the phi fields with del mu phi replaced by d mu phi. Kinetic terms for the gauge boson field with field strengths d mu a nu minus d nu a mu, which we called f mu nu. Quadratic and quartic terms for the scalar potential. So as much as we make the model more complicated, we go from discrete to U1 to SO3 to local U1. Somehow all of them give almost the same form of the scalar potential. And so I will not repeat this, it's written. I will not repeat this, it's written. I will repeat this. We choose mu squared smaller than 0 because we want the model to exhibit spontaneous symmetry breaking, because that's what we want to understand what happens. we define v squared is minus mu squared over lambda. And so phi must get the vacuum expectation value v over square root of 2. And now we do a trick, okay, which contradicts one of the rules that I put, I guess, in, I don't know, in the, almost one of the first, the rules of the game. There were 8 rules, and one of them is that we write terms that are always polynomial in the field. And now I'm going to write something which is not a polynomial in the field. Phi has 2 degrees of freedom, h and psi. Before I used h plus I psi. Now I use something different because it makes my life easier. E to the I psi over v times v plus h over square root of 2. Why do I do that? You don't have to follow the details. You don't have to understand everything. But the potential of psi is flat. I remember that h was the direction in the sombrero of going up, and psi was the thing in the bottom, the circle. And all the circle is flat. It's around, so there is no preferred point in that minimum. And so I'm allowed in that case I can expand anywhere. And in addition, the first term here is 1 plus I psi, and when we multiply that with the v plus h, we get the same first term that I got before. So I'm allowed to do it. It makes my life easier, and psi will anyway soon disappear from the Lagrangian. And so you may worry about it. It's a little bit tricky, but that's the simplest way of doing things. Now, this was a symmetry of the Lagrangian originally. But when we expand around the minimum, it's no longer a symmetry of the Lagrangian. What it is a change of basis. Okay, so we used before changes of basis. We went from a basis of a generic mass matrix to one where the mass matrix is diagonal. This is another way to make a change of basis, to multiply phi by phase. No longer symmetry, but a change of basis. So now I do the trick. It's a legal trick, okay? It allows me to do a shortcut, but it's a legal one. So I choose this transformation with theta, specific value of theta, phase space function. So theta is mine. I choose this to be minus psi of x over v, where psi of x was this second degree of freedom. Again, it's legal. And so if phi was defined this way, and I give it a transformation e to the minus psi over v phi, then the transform field has no psi in it, just v over h. But psi did not disappear completely from the Lagrangian, because there is a transformation law of A mu, which includes the derivative of this phase, and this phase is minus psi over v. And so A mu transforms into A mu plus 1 over gv d mu psi. That was the rule of how gauge bosons transform under a local transformation. And I call this combination v mu. So when I write v mu, implicitly there is a psi field in the theory. We don't see it because I gave it a new name. And actually we see that v mu consists of the original mu, of its 2 degrees of freedom, but also depend on psi, which was another degree of freedom. And so d mu psi is, so mu has 2 polarization, d mu psi precisely provides this longitudinal polarization that we missed. So we will not see psi anymore in the Lagrangian, but the place where it does appear is wherever we see a v. It has in it a new degree of freedom that was not there before, a third degree of freedom, which is the space-time derivative of psi. I know this is complicated, so this comes a little bit out of the blue. So the important thing will be the bottom line and not necessarily the way I derived it. So this is the Lagrangian. starting from redefining phi to be this way, doing the change of basis this way with this choice of rotation or transformation angle, and this is how it looks after that. Kinetic term for the V mu field. For this term, it doesn't matter whether we use V mu or A mu, because d nu V mu minus d mu V nu is, this term will vanish from there, okay? So it will not appear, but this is, if you want, defined in terms of V mu. A kinetic term for the H field, a mass squared term for the vector boson field. I should now not call it anymore gauge boson because it's different from A mu. It has 3 degrees of freedom. It's a vector boson. It's still a spin 1, but not gauge boson. And it has a mass squared term, which was not that before. A mass squared term for the field H. Interaction terms of 2 vector boson with the scalar field, or 2 vector bosons with 2 of the scalar fields, and 3 linear and quartic terms for the scalar field. So, this is now the interpretation. First, what is the spectrum described by this Lagrangian? It has a massive vector boson. We read it from here. The mass squared is GV squared. It's proportional to V. If we had no vacuum expectation value, it would have been 0. It must be proportional to V, okay? Because V is the thing that breaks the symmetry. If the symmetry were not broken, all the vector bosons of the theory would be massless gauge bosons. Only allowed because the symmetry is spontaneously broken, so V must appear here. We have a massive scalars, 2 lambda V squared. The field psi does not appear here explicitly, but it's hidden within the V mu, which is A mu plus d mu psi times the number. So it's hidden within d mu psi is part, it's the 3rd degree of freedom of the massive vector boson, and the number of degrees of freedom is not changed. What was 2 degrees of freedom for a gauge field and 1 degree of freedom of a scalar field became 3 degrees of freedom for a massive vector boson. This is the Higgs mechanism. So, I told you before that the only way to incorporate spin 1 in a mathematically consistent way in the Lagrangian is if they are gauge bosons. Gauge bosons are, however, predicted to be massless. So there was a question, how do we explain elementary massive vector boson? And 2 papers, 3 papers, Higgs in 1 paper and Broughton and Glare in another, came with this solution. If there is a spontaneous breaking of a local symmetry, then the gauge bosons that correspond to the broken generators become massive. That's the mechanism. That's why it's called the Broughton and Glare Higgs, or BEH field. That's the consensus now of the community, after a long fight by the Belgian community, because it was for a long time called the Higgs field, and Broughton and Glare deserve name to be recorded because it was roughly simultaneous. What Broughton and Glare did not realize, but Higgs did, is that this spontaneous breaking is accompanied by a massive scalar field, which is the scalar in the direction of the vacuum expectation value. Okay, in a complex plane, this is the direction. So the particle that is related to that, this scalar, got the name, the Higgs boson, and this name remains. Actually, the gossip, I don't know, I didn't do particle physics in 1964. I was already born by there, but no idea of what particle physics is. The gossip is that Higgs also didn't realize that there is a particle that, and the referee told him when he submitted his paper that there is a particle accompanying this, and then he added it to his paper, and now, the Higgs boson is the main program of the LHC and the most dramatic discovery of the 21st century in particle physics, carries the name of Higgs. With acknowledgement to the referee, whom I have no idea who he was. It's not the only case, I think, in history of referees or other things making a contribution that leads to a Nobel Prize. I think not exactly the same, but another kind of interesting story is the fact that I mentioned before of the running of the QCD coupling constant, the sign of the beta function. So it got the Nobel Prize to 3 people, Politzer, Gross, and Wilczek. Politzer, in the paper, he was a student then of Sidney Coleman, and he wrote an independent paper showing that. And another paper was by Gross and his student Wilczek, showing that the sign is negative with all the consequences. And I don't know if it's a gossip, I think this is a true story. So actually, Gross and Wilczek told about their calculation. They had the wrong sign in their calculation. They got a positive sign instead of negative. They told it to Coleman, who was Politzer advisor, and Coleman told them, no, you have the wrong sign. They corrected the sign, and the 3 of them, Gross, Wilczek, and Politzer, got the Nobel Prize. Coleman did not, so acknowledgement to Coleman. So these things happen. Actually, again, this collaborator that I mentioned, Helen Quinn, she was a friend of Politzer. He was a professor in Caltech, and he told Helen Quinn that this paper and the Nobel Prize are the disaster of his life. It completely ruined them, because after this paper, everyone expected him to do things very high level, and he felt that he did this paper, it's very nice, but these expectations kind of, he thought, are beyond his abilities, and he was not very happy Nobel laureate professor at Caltech. So it's nice to know that there are also such people in the community. If I'm not, my picture, a movie is taken, so I will not say anything about Gross and Wilczek in this context. Okay. So it's all gossip, okay? I don't know if it's true or not. That's for the record, please. Okay. So we have the original Lagrangian, which has 2 parameters, mu squared and lambda, and 2 terms that are not kinetic terms. Kinetic terms don't have, d mu does have in it G of the coupling constant of the gauge group. And here we have, 1, 2, 3, 4, 5, 6 terms, and yet the dependence is on the same 2 parameters. So it means that there are here 4 relations among these 6 terms, because they depend on 3 parameters, right? G, V, and lambda. And these 3 relations, if you see that they are realized in nature, these are the physical particles that you observe, right? H, a massive vector boson V, and you measure all the terms related to them, and you discover that there are these 3 relations. Then you understand that there is here spontaneous symmetry breaking, that this is not the most general model of a vector boson and a single scalar field, in spite of the fact that all terms that are here, that are allowed, appear here. So it's again, same predictive power. The predictions are different. The coupling of the Higgs to 2 vector bosons, which appear here, which appears here. It's G squared V, which can be written as the mass squared of V over V. So it's proportional to mv squared. That would be very generic in the couplings of this Higgs boson to all particles, as we will see. And as before, dimensionless couplings, now we have 2 of them, the quartic Higgs and the 2 vector boson 2 Higgs remain unchanged. It's a renormalizable theory. So, I think that's summary? No, not yet. Okay, so what we learned about spontaneous breaking of local symmetry. It generates masses for the gauge bosons related to the broken generators. We did not see that if it's broken to a subgroup and some of the generators are not broken, that these vector bosons remain massless. We'll see it when we discuss the leptonic standard model and the standard model. So it's written here, gauge bosons related to unbroken generators remain massless. We did not see it, we will see it. The number of parameters is the same for the symmetric and spontaneously broken theories. And this is, again, a point which in retrospect is maybe trivial. The field that gets a vacuum expectation value can be only a scalar field, a field that doesn't transform under space-time transformation. If you give a vacuum expectation value to a fermion or to a vector boson, you are breaking Lorentz invariance. So don't do that, okay? We want to keep that. That was one of the rules. So it's always scalar field. With almost all theories, what will be allowed when imposing a symmetry is a quadratic and quartic terms for the scalar, and so the mechanism as far as the scalar potential looks like is the same, local or global, and U1 or SU3 or SO3, whatever, it's almost always just these two terms, mu square negative, lambda positive, and you go on from there. Yeah, this is just saying that if in the model that we did not have fermions. If we had fermions and they would have been chiral and charged, there would be no mass terms in the original Lagrangian. If you add fermions and their charges would be equal to, or the difference would be equal to the charge of the scalar field, then you could have a Yukawa term. You could not have bare mass terms for the fermions. Now you replace phi with this combination that I chose. You do this basis change, and what you get is again a mass term as we did in the global case. So there is no real difference. This is just to say that Xi also disappears from the Yukawa. Okay. Yeah, the last point is what? So I presented this table before in the introduction, but now I think we've seen all of these. What are the main things, not the only things that symmetries do? Space-time symmetries, E, a result of time translation invariance, momentum, so energy, momentum, the result of space translation invariance, angular momentum conservation, a result of invariance to rotations in space. Discrete symmetries imply selection rules. Global symmetries give conserved charges. If they are spontaneously broken, there are Goldstone bosons, massless scalars accompanying that. Local symmetries predict interactions mediated by massless spin 1 particles. Spontaneously broken local symmetries imply interactions mediated by massive spin 1 particles. So hereby vector particles with 2 degrees of freedom and here with 3 degrees of freedom. And again, the lightest charged particle under a symmetry is predicted to be massless. Chiral charged fermions are also massless in the case of spontaneous breaking if they are chirally uncharged under the original symmetry, but either not chiral or neutral under the symmetry that is not spontaneously broken. They may become, they do not necessarily become massive. The standard model would be an example of particles that after the spontaneous, that are chiral and charged in the original symmetry and are neutral singlets of the full unbroken symmetry after spontaneous symmetry, yet they do not gain masses. These are the neutrinos, and we will understand more or less why they remain massless in spite of being neutral, so they could have in general Majorana masses, yet they do not gain Majorana masses after the spontaneous breaking. So this may happen, it does not necessarily happen. What time is it? 4:25. I think in spite of having 5 minutes, we will not start a new chapter. The next chapter is as heavy as this one was. It's a model. Okay, so I'll give just an introduction of. It's a model that I call the leptonic standard model. It's part of the standard model. It includes all the leptons of the standard model, and it includes the weak electromagnetic and Yukawa interaction. What it misses compared to the standard model is quarks and strong interactions. And I take this intermediate step because, first of all, it's complicated enough. And second, it will be the first time that we incorporate all the three ingredients that we exposed in the few lectures that I gave. That is, it will include an abelian local symmetry, a non-abelian local symmetry, and spontaneous symmetry breaking. And we will see there how all of this plays together and what kind of phenomenology it gives. So that's tomorrow morning. Let's stop here.
Online in the morning session, we can speak. By Debabrata Sahu, why we do not need to go above SU2 or SU3?
Yeah. We don't need to go above SU3 cos SU2 because that is what we have encountered so far in nature. We see 12 vector bosons, it's not the right counting, but we see 8 massless gauge bosons that we identify as the joint representation of SU3, that's the gluon. And we see 3 massive gauge bosons and 1 massless gauge boson that we identify as coming from an SU2 symmetry and a U1. So the interactions, we said that we learn about the gauge symmetries, if we want to go historically, from the vector bosons that we see in nature. We say that the only way to incorporate vector bosons in a mathematically consistent way is via symmetries. And since we see this octet of SU3, if you want, it's a little bit more complicated. We'll see tomorrow a triplet of SU2 and a single one corresponding to U1. Then what we need to describe all of these interactions is SU3 cross SU2 cross U1. It doesn't mean that nature doesn't have additional symmetries. They must be additional gauge symmetries, local symmetries. They must be, in some sense, spontaneously broken so that the related gauge bosons turned into massive vector bosons and their masses are above the reach of our experiments. So that could be, and indeed, in the theories called grand unified theories, there is a larger gauge group that has SU3 cross SU2 cross U1 as a subgroup. The smallest grand unified group is SU5. The next largest one, so SU5 has a subgroup SU3 cross SU2 cross U1. So of the 24 generators of SU5, it means that 12 must be spontaneously broken to give SU3 cross SU2 cross U1, must be broken at a high scale, and then additional ones within SU3 cross SU2 cross U1. 3 more are broken to give the masses to the W plus, W minus, and the Z. The next one is SO10, which has SU5 as a subgroup. The next one is E6, which has SO10 as a subgroup. and there is another direction which is somewhat different, SU3 cubed times Z3, which relates the three SU3 to each other. That's also a grand unifying group. So all of these are larger gauge groups, spontaneously broken, that could be there in nature, but so far we do not have any evidence for that. So for whatever we have evidence, SU3 cross SU2 cross U1 is enough. Also, as I mentioned yesterday, it's a curious fact that all the fields that we observe in nature so far are in all the fermion and scalar field are either singlets of the gauge group or in the fundamental representation. Triplets or singlet of SU3, doublets or singlets of SU2. That's also not necessarily the case in nature. Maybe there are higher representations, also for scalars and fermions. This is almost unavoidable in grand unified theories because to break the large unifying group into SU3 cross SU2 cross U1, you need scalars in higher representations, not just the fundamental. And also for SU5, for the fermions, you can just have the standard model fermions. SO10 is interesting because in the standard model, as we will see, each generation call has 15 degrees of freedom. SO10, all of these fit into one representation of SO10, which is of dimension 16. So it has one more degree of freedom, and its quantum numbers under SU3 cross SU2 cross U1 is a singlet. It doesn't transform under this subgroup. It transformed under the SO10, but not under this subgroup. We would love to have such a particle because that could be what we call a right-handed neutrino and realize the seesaw mechanism that you may know. So we need a right-handed fermion that doesn't transform under the standard model gauge group in order the simplest mechanism to explain neutrino masses. So, and 16 is not the smallest representation of SO10. So, yeah, there are to go beyond, we need hints from nature. We may speculate theoretically, but so far, no need by what we observe in nature.
So we got to know that the Higgs mechanism tells us how we get the massive bosons.
Again, sorry?
So I'm saying that by Higgs mechanism, we know that how we are getting these massive bosons by the weak interactions.
We did not yet see it in the context of the weak interactions, and we will see it tomorrow.
So, is there in the Higgs mechanism? Can we get to know what will be the mass, like what amount of mass will be generated, the magnitude?
So, in general, no, it depends on the parameters of the theory. So, in the scalar potential, it depends on mu squared over lambda. What is the scale? So, we know that the mass will be proportional to V, the vacuum expectation value of the scalar field that has a minimum not at zero value. And so, a priori, you have to measure something, but we get hints, okay? So, well before we discovered the W and the Z boson directly, well before we produced them in the in our accelerators, we could tell their masses. We'll see that actually, because, for example, at that time, when experiments were held at much lower energy, then there was an effective coupling of 4 fermions. It's called G Fermi. I don't know how many of you encountered it. So muon decay, when we calculate it in a theory that has not directly the masses of the W boson, that's mu going to E, nu, mu, there is a coupling constant there that we call G Fermi. In the full theory that includes the W in the Z and the full standard model, this G Fermi is just proportional to 1 over V squared times a number, where V is the vacuum expectation value. So from G Fermi, we know the value of the vacuum expectation value, okay? An experiment done in the 100 MeV scale, that's muon decay. We could tell that the vacuum expectation value of the standard model is 246 GeV, okay, much higher. And the theory will tell us that the mass of the W is this times coupling constant G of the weak interactions. So if we measure by other processes this G and multiply it by V, then we know, or G over 2, then we know what to expect of the mass of the W. So there are ways to know it before, but for that you have to make several measurements that will tell you the ingredients that, so the vacuum expectation value and the gauge couplings, then you can tell.
Did somebody else ask my questions?
Go ahead.
Okay, cool. So yeah, my question was like, we saw that the vacuum expectation value of the Higgs boson is dependent upon the coupling constants of the original field theory, right? The quartic and the quadratic ones. So like today in the morning, we learned that the coupling constants run with energy scales, right? So can the vacuum expectation value of the Higgs boson also change with energy scales?
So, okay, it's a little bit confusing what you ask, but I think not. The vacuum expectation value is a fixed number. Yeah, G typically you measure with processes like this, and they have radiative corrections coming, and these radiative corrections are encoded in the running. The leading order effect can be just embedded in an effective value of G running. So there could be, for example, here a loop correction to this, and the calculation then depends on the energy related to these processes. V does not have a similar thing. It's not part of a process. So it's a fixed number. What I have to think is, okay, it's minus mu squared over lambda, but at what scale? Okay, so the answer is no. I don't know to say now off my head why it is no. V doesn't run, okay? G does run. I hope to be able to answer it better tomorrow, maybe.
I have a question related to Goldstone boson. See, we have a global symmetry and there's a conservation of charge, and then the gauge boson arrives because of the local symmetry is imposed.
Yes.
And so where are Goldstone bosons basically, and what are the physical significance of it?
What is the physical significance? Well, I would say that the main thing is that it provides a possible explanation if we observe massless scalars. Now, among the elementary particles, there is just a single scalar that we know, which is the Higgs boson. It's not massless, so it's not a Goldstone boson. But it helps us, for example, to understand the lightness of the pions. So there are these three lightest mesons, pi plus, pi minus, and pi zero, with a mass around 140 GeV. And we understand that as a spontaneous breaking of an approximate global symmetry of the strong interactions. And this explanation provides us with understanding why there are 3 of these that are the lightest, why there are 8, which are including the kaons and the eta, which are also relatively light, and why they are not exactly massless, but only very light. So also that can be explained. And so it gives us an understanding of some of the spectrum of the hadrons. So that's the main thing that now is used, or that the Goldstone theorem applies to. Now, there are models suggested by theorists, for example, that lepton number is spontaneously broken in nature, a global lepton number, and that would require that there is a Goldstone boson related to that. In the terminology of the community, this is called the Majoron, and you can predict, if indeed that's the case in nature, you can predict what should be the ways to discover such a Majoron. It was not discovered. Probably there is no spontaneous breaking of lepton number, but in theoretical models, this is a possibility. So, yeah, it's our best hint of why, if we observe very light scalars, or in particular massless scalars, it's a hint for a spontaneously broken global symmetry. We do not observe massless, and as I said, among the hadrons, we observe very light ones in some sense, and that is explained actually by the Goldstone theorem. Both their lightness and the fact that they're not exactly massless. Not exactly massless is an additional complication of this, which I will not go into.
Okay. Thank you.
My question is about the unitary gauge transformation in the Higgs mechanism, unitary gauge transformation. The Higgs mechanism.
The Higgs mechanism should to go
Yes.
to the transparency, or here
Yes,
you want
you can go. It will be better.
Hmm?
You can go to the Higgs mechanism slides, so it will be better.
Okay. You tell me where to stop.
No.
Higgs mechanism slide, right?
Yes. Unitary gauge. No, unitary gauge. Unitary gauge slide, I think. No. Next
Go.
slide, I think.
Sorry, I don't understand. Go on, or
Next slide.
next
slide.
one?
Yes.
Okay.
Where is the unitary gauge? Okay. But my question is why you need the unitary gauge transformation at the first place?
Why do I?
Unitary gauge transformation. The ifs.
Why do I need? I don't understand what.
I think you want transform? No.
So I think he's asking, why do you need to stick to unitary?
No. In the next slide, I think I'm not sure of the slide about.
Why do I need what?
I think next slide. The
Next time. Okay.
remember. Yes. This slide. Why you need this unitary gauge actually? In the first place, if we
Yeah. So the unitary, I could do it in any case. So I could do a different transformation or not do transformation at all. The symmetry, the physical consequences would be the same. The useful, as I said, different bases are convenient for different things. In the unitary gauge, in the end, all the fields that appear explicitly in the Lagrangian are related to the particles that you observe in nature. So this has a scalar field, which is the Higgs scalar, and a massive vector boson V mu, which is the physical vector boson. You could do the same physics in the previous language, where you have H and psi and A as 2 degrees of freedom. You could do the same, you would get the same physics, but in a much more complicated way. You would have explicitly A mu and D mu psi in your Lagrangian, you will see that they always appear in a specific combination, and the interpretation of that, getting to the fact that actually together they represent an active vector boson, is a more complicated way. So if you want to understand straightforwardly, let's say, or in the simplest way, the spectrum of your theory and the interaction, the best way is to go, or to understand the phenomenology, what I would say. For me, the spectrum and the interactions are the phenomenology. Then the most convenient way to do it is the unitary gauge. In the unitary gauge, you see each particle, elementary particle in nature, related to a field, and not, let's say, a particle of mass 80 GeV is the W, it's a combination of two fields. The unitary gauge, you see it as one field. And the scalar field psi that appears here, you would understand that it doesn't have Yukawa couplings, it has flat potential, it does not appear in the scalar potential, it appears only with the derivative d mu, and so it would be more complicated to interpret what it is. In the end, you would find that it's the longitudinal degree of freedom of a vector boson, but it's a longer way than just going directly to this choice of fields that is here and the unitary gauge. So it's just a simplifying way. Yeah, it's a cousin of what I answered yesterday about whether to use the mass matrix that was, I don't know, 2 by 2 or 3 by 3 with all entries, or go to the diagonal basis, the mass basis. For phenomenology, there is a basis which is the most convenient. Here, so it's the mass basis for fermions, the mass basis for scalars if you have several, and the unitary gauge to understand vector bosons versus scalars. That's the most straightforward way. But all of these, you could use different bases and get the same phenomenon, the same physics. So just whether it's simple or not.
This vacuum expectation value is made of these mu and lambda parameters, right? So would not
The
it
vacuum
be
expectation
Yeah.
value should obey this
so
equation.
would not it be better that it changes when we change the energy scale? I mean, in the running, because it's mu and lambda,
no,
and
so I
mu and
think-
lambda themselves should vary.
Yeah, I think that this combination, mu squared over lambda, doesn't change. So it's a fixed value. But as I said, let me think about it and come with a better answer on this issue.
There's one online question again by Priyanshu Bansal. To incorporate these, I think it refers to the previous question that was there. Why we do not need to go above SU2 or SU3? To incorporate these into larger groups, do we have to go to higher dimensions as in string theory?
To higher dimension S?
To incorporate these into larger groups, do we have to go to higher dimensions as in string theory?
Oh, to higher space-time dimensions?
Yeah.
No. So the grand unified theories are four-dimensional models. No need to go to higher space-time dimensions. This is all within quantum field theory, not string theory, all of this, including grand unification.
So in the continuation of his question, I want to ask, in the continuation of the previous question of higher dimensions.
Yes.
So up to now we are dealing with only renormalized Lagrangians. Means dimensions are less than or equal to 4 up to now. But
sorry, you should speak louder.
Okay.
Put it closer to your mouth, perhaps.
In the continuation of the previous question, who asked about the higher dimensions. So I just want to remember.
How dimension the representation?
Yeah.
Oh.
So up to now we are dealing with only that kind of Lagrangians which are renormalized. Means dimensions should be less than or equal to 4.
Well,
Okay.
as long
Are you understand?
Yes.
Yeah, up to now we are dealing with only that kind of Lagrangians whose dimensions are less than or equal to 4. And even in symmetry breaking case, we have considered or dealing with only that kind of Lagrangians. So my question is, in what case we can deal with non-renormalized Lagrangians? With dimension can be higher than 4.
The dimension of the terms in the fields can be higher than 4.
Yeah.
So that's when the theory is an effective theory and not a full theory of nature, and has a scale of energy above which the theory is not valid anymore. Okay, so again, once you go, let's say you have a phi to the fifth term, it has a coefficient which I write as 1 over lambda. Lambda is an energy scale. It must be high compared to the scale at which you do experiments. If you try to make a calculation involving this term with energy scale higher than lambda, that's not a good idea. The theory there is not valid. So this scale is the cutoff scale of the theory. And if you have such a cutoff scale, then you should include non-normalizable terms. If the theory has a pretension to be valid up to arbitrarily high energy, you cannot have these terms because they will give you inconsistent results.
Okay. So actually I have another question also. Might be it can be a silly question. Here mu square and lambda are real.
Yes.
And mu square is less than 0 you are considering.
Yes.
It's a square term. How it can be less than 0?
Then,
He said that you cannot take away the square term.
yeah.
Okay.
So this is the name. Okay. If you prefer, let's replace mu squared with, I don't know, x. Okay, and write the quadratic term as x phi dagger phi. And now x can be positive or negative. I said that mu squared is not the square of mu. Okay, it's not the square of anything. It's just dimension 2 in mass. And this is confusing because we are used to see such a thing as the square of something. This is not the square of something. It's the name of the parameter. The parameter is mu with super index 2. Okay, I should not call it mu squared. I should call it mu with super index 2. Okay? And or call it anything you want.
Okay. Sir, we already know the standard model is not a complete theory.
So again, slowly.
We already know that standard model is not a complete theory. There is some.
The standard model? Indeed, it's not a complete theory
So
of nature.
why not we should also include this effective operator? Because we already know that it is not a complete theory.
Okay, so as I said, usually as long as we are doing experiments at a scale that is much lower than the cutoff scale, then the renormalizable terms are a good approximation for the processes that we are calculating. And as long as we do not see a deviation in measurements from the prediction of the renormalizable terms, we do not have to invoke the normalizable terms because they may be too small. However, as we may see on Thursday or Friday, neutrino masses are inconsistent with the renormalizable standard model, and very likely they come from dimension 5 terms. And for neutrino masses, we should invoke the normalizable term, and I will not write it in that model. And actually, if neutrino masses are at present the only hint that we have, or the only thing that requires non-normalizable terms, then we get an idea of what the cutoff scale is. And what neutrino masses suggest is that the cutoff scale is of order 10 to the 15 GeV, also known as the seesaw scale. And that means that not including the renormalizable, non-normalizable terms is good to order roughly V over lambda, so the corrections are of order 10 to the minus 13, which is a very small correction. The exception is for non-normalizable terms that break the accidental symmetries of the standard model, the renormalizable standard model, which is what these dimension 5 terms do. They break lepton number, which is an accidental symmetry. Because in this case, the leading term from the standard model is 0. And so this is not a small correction to the standard model. This is it. This is the leading term for neutrino masses. So normalizable terms that break standard model accidental symmetries should be included. So if you observe neutrino masses, you should go to dimension 5. If you will see baryon number violation, you should go to dimension 6, because dimension 5 terms do not break baryon number. So if we see the proton decay, you must include dimension 6, and then you will get another hint. So these terms will be of order v squared over lambda squared, but as a dimension, but again, this will be a correction to 0. So it's not 10 to the minus 26 compared to something that the standard model gives you. It's a correction to something that is 0. And so I would distinguish non-normalizable terms that breaks accidental symmetries. They are small. Neutrino masses are very small compared to all other things. So they are small, but they are the leading term for observables that break the symmetries, compared to things that just correct the standard model calculation. And if the scale is 10 to the 15 GeV, then it's a negligible correction. And so we already, in any way, neglect quantum gravity effects because we don't know how to calculate them, but also because these are very, very small corrections as far as we can tell. They're roughly v squared over the Planck scale squared. So in any case, we are, from the beginning, neglecting something. And yeah, so that's...
Anyone else?
Next time to
Good.